Okay, so I'll be talking about salinity and rapidly intensifying tropical cyclones in the Atlantic. And there are a couple of motivations for this. So one motivation is that rapid intensification is very difficult to predict, especially in the Atlantic. And the other is that salinity has not been considered really in the past in terms of a potential predictor for intensification. So the idea was that maybe salinity could be a useful indicator of whether rapid intensification might occur for Atlantic hurricanes. And this is work that I've done with John Kaplan, who's in the Hurricane Research Division here at AOML. Also several colleagues at ENNL in Washington State and at Ephemer in France. All right, so first we need to get some definitions. So rapid intensification generally is defined as an increase in intensity of at least 30 knots over a period of 24 hours. Some people have also used 25 knots over a 24-hour period. This is generally the 95th percentile of intensity change over the water over a 24-hour period. And so this is a pretty, not a common occurrence, but it's very impactful when it happens. The probability of rapid intensification is about 31% for all tropical cyclones. It happens a little less than 1/3 of the time overall. For hurricanes, it goes up to 60%. 83% of all major hurricanes undergo rapid intensification at some point. And basically all Category 4 and 5 hurricanes undergo rapid intensification. So, of course, these are the most dangerous ones. So in order to predict these hurricanes, it's useful to understand rapid intensification and to be able to predict it. In terms of where rapid intensification is most likely to occur, it's most likely to happen at low latitudes. This is where SST is higher. Also, it tends to be in the Western Basin, also, again, where SST is highest. The locations of rapid intensification are shown here for two different periods. And the number of locations, so the frequency of occurrence of rapid intensification has not changed over the past 30 years. They're the same number of dots, basically, in each of these plots. But the magnitude of rapid intensification has increased significantly from this earlier period to the later period. And you can see this, there are a lot more yellow and red and purple dots in the later period, the plot on the right, compared to the plot on the left. So this is another reason why it's important to understand rapid intensification and be able to predict it. This can be very dangerous if these hurricanes intensify rapidly before landfall. This is an example, Hurricane Michael. The official forecast is shown on the left, and it was predicting about 2 days before landfall that the intensity would be a Category 2, so not even a major hurricane, and of course it ended up rapidly intensifying to Category 5 before making landfall. Okay. And there is some hope for being able to predict it, and it can be predicted to some extent. The main indicators, there are two from the ocean. So one is the maximum potential intensity minus the current maximum wind speed of the storm. So the greater value of this, the more potential the storm has to intensify and reach its maximum potential intensity. This is a strong function of SST. The second one is ocean heat content. We know the subsurface ocean also matters. The third on the list here is persistence, just the intensity change during the previous 12 hours. And then the last 7 here are atmospheric predictors, including wind shear. Low wind shear is conducive to rapid intensification, upper level divergence, the spatial pattern of convection. So if there's more convection to the northwest of the storm, this tends to be conducive because the storms generally move to the north and the west. Total precipitable water, more humid More water is better. Inner core dry air, less of that is better, and more variability of cloud top brightness temperature. And you'll notice that there's nothing in this list that deals with ocean salinity or ocean stratification in general. Okay, so with those indicators, how well can they actually indicate the probability that rapid intensification will occur? So that's what these plots show. Again, this is from one of John Kaplan's papers. And what this does is it takes each indicator and it scales it from 0 to 1. So 0 means it's not conducive at all to rapid intensification. For example, SST of 20, that's lower than any SST ever observed during rapid intensification, so that would get a value of 0. And a value of 1 would be for SST, let's say, of 33, because that's at the uppermost end of SST that's been observed for rapid intensification, and then the rest it's scaled in between. So if you add up all these scaled predictors, that's what's shown on the x-axis in terms of quartiles, and the y-axis is probability of rapid intensification being observed. And so at the left, a value of 0 means that none of the indicators is conducive. And of course, we get a 0 probability of rapid intensification. As we go to the right, in the upper quartile, there's about a 70% chance of rapid intensification. So this is basically all of the predictors are conducive to rapid intensification, or most of them. So even with these good indicators, it's still not a sure thing. It's about 70% that you'll get rapid intensification. And the dashed lines show the climatology, so about 5 to 10% on average. And that's the Eastern Pacific. In the Atlantic, the situation is worse. If you look at the upper quartile, there's about a 50-50 chance that rapid intensification will occur if you have very conducive conditions. So it's difficult to predict, of course, rapid intensification. And this shows more quantitatively the skill of detecting rapid intensification. So if you have these indicators, you want to say, is rapid intensification going to happen or is it not? And that's what this does. So the red bar here is from a statistical rapid intensification index that John Kaplan developed. And it shows some different metrics. So probability of detection is the number of successful forecasts divided by the total number of times that RI actually occurred. So you want this to be high. And the probability of detection for the statistical model, the red bar, is about 50%, and it's much lower for the official NHC forecast and from the GFBL numerical model. Of course, if you always predict RI, this will be 100%. So the false alarm ratio is important. This is the number that are forecast but not observed, divided by the total number of forecasts. So about 60 to 90% of the time, these models are able to, or 60 to 90% of the time they predict it and it actually doesn't happen. So that's a pretty high number. The bottom shows the skill score. So take the probability of detection minus the probability of false detection. If this is greater than 0, it has some predictability. The statistical model has some predictability. The official forecast has a little bit, and the GFDL model has none. So again, a difficult thing to predict. This is for the Atlantic. As we'd expect in the Eastern Pacific, the predictability is better. And it's not known exactly why the Eastern Pacific is more predictable. It's possible that there's just a smaller region where the SST is very high, and you can get all these predictors lining up and giving indicators that it's very conducive. All conditions are very conducive. Where in the Atlantic, it's more spread out, and you can have different conducive and not conducive conditions for the different predictors. So based on how difficult it is to predict rapid intensification and how important it is to be able to predict it, it's a major goal of the Hurricane Forecast Improvement Project to increase the probability of detection to 90% and decrease the false alarm ratio to 10%. If you look back at this, you can see this is a very ambitious goal with currently probability of detection about 50% and false alarm ratio of 70%. So this would be a big improvement. And also the focus on RI change is the highest priority forecast challenge identified by the National Hurricane Center. All right, so that was some background on kind of what rapid intensification is and how predictable it is. Now we'll get into the ocean, how the ocean might impact rapid intensification. So this shows mean conditions during the peak of the hurricane season in September, tropical cyclone heat potential, which is the integral of ocean temperature from the surface down to the 26-degree isotherm, so a measure of heat content. And the mean value for rapid intensification is about 55. So pretty much all of the orange in this figure, on average, conditions are conducive, at least in terms of the ocean, for rapid intensification. This heat content decreases eastward from the Caribbean into the Western Atlantic. What this doesn't account for is salinity. This is just temperature. So the question is, given this big low salinity plume from the Amazon and Orinoco rivers, could this be an indicator of rapid intensification in addition to the well-known temperature-based predictors? All right, so this is a case study from one hurricane, Hurricane Katia, and it passed over the northern extent of this low salinity plume in September 2011. As it passed over, there was a big increase in surface salinity as it passed by, about 1 to 2 PSU. And there was a very muted SST cooling as it passed over the plume. And then there was a lot more cooling as it went past the plume. That's shown also on the left. On the right, this shows a different way of looking at it, where the storm is moving. So this is time on the y-axis and longitude on the x-axis. So as the hurricane moved westward, to the left in this figure, you can see the surface salinity in the top panel. The surface salinity increased and maintained higher for at least a couple of weeks afterwards. And the bottom plot shows SST. SST really didn't cool a lot over the plume in the middle of the figure. And then as soon as it got outside of the plume, there was a big increase in the SST cooling. So the idea is that salinity can potentially, through the additional stratification, and diminish mixing and reduce cooling, and this can help to feed back positively to the hurricane's intensity. But that was only one case. This study here looked at all of the tropical cyclone locations in the Atlantic and separated them into being over the plume or in the open ocean. And the main result, consistent with this case study, is that when tropical cyclones are over the plume, there's a significant reduction in the SST cooling that they cause compared to when they're over the open ocean. And it's more pronounced for slow-moving storms than fast-moving. And it's more pronounced for stronger storms compared to weak ones. Major hurricanes especially have a big reduction in the SST cooling when they go over this low salinity plume. And the right panels show why this is the case. It shows the mean salinity, so it's depth versus latitude averaged in the plume longitudes 50 to 60 west. There's a very shallow and strong salinity stratification south of about 20 degrees north, which inhibits mixing. And if you take the 26-degree isotherm, the gray line, take something like tropical cyclone heat potential or heat content, this will not properly account for this additional stratification from salinity. The bottom plot shows the density stratification. So most of this density stratification is being caused by salinity, not temperature. And if you look at the latitude of maximum stratification averaged in the upper ocean, a little south of 20 degrees north, this is also where we see the peak in the number of Category 4 and 5 hurricanes that go across the plume. So that's observations. There's a recent modeling study which used a coupled model and looked at an ocean that had strong salinity stratification, a barrier layer of 30 meters. So this indicates a big separation between the density-based mixed layer and the isothermal layer, and minus a simulation with no barrier layer, no salinity stratification. And the result is that there's a lot less cooling caused by the hurricane when you have this salinity stratification. It shows a reduction in cooling of on the order of 0.5 degree or so. And it's similar for the slow-moving and kind of the medium translation speed cases. And so this is a couple model, and they found that associated with this was about a 10 to 15% increase in the intensity of the storm compared to when there's no salinity stratification. The last thing on this, the right panel shows the observed number of tropical cyclones that intensified locally in category 4 or 5. There's the maximum over the northern part of this low salinity plume. So this is supporting these other results, at least in terms of observations. Okay, so in summary, for this part, so past research shows evidence that shallow salinity stratification reduces SST cooling and increases the likelihood of intensification. There are many studies now showing this. The biggest impact seems to be for stronger storms, especially at least category 1 intensity. So the question that I'll address is, the main question is, can this be useful for prediction? So if we reverse this and say, instead of taking a certain ocean condition, and how does it affect the SST cooling and the intensity, if we take different intensification rates, for example, rapid intensification versus non-RI, are there significant differences in salinity? And if there are, then this indicates that it could be possibly a good predictor of when rapid intensification might occur. All right, so now I'll get into our results. So first, another case study, but this time we'll be looking at the intensification rate instead of the intensity. So this is Hurricane Irma, a well-known hurricane that moved to the west. It intensified rapidly, where I've circled here in black, to the east of the Caribbean. And this happened in a region where SST was increasing to the west. The tropical cyclone heat potential was increasing westward, and there was a big decrease in salinity over the plume. The right panel show the conditions along the track of Irma, going from east to west. So, and then the colored circles are the rapid intensification. So, as I said, so the SST increased, and the top panel, the heat potential was also increasing, and there was a really big decrease in surface salinity, going from about 37 down to about 34 as Irma intensified rapidly. So the question is, in general, is this the case? Is salinity a good indicator? And to look at this, we know that salinity will affect the tropical cyclone ultimately through SST. It reduces SST cooling under the storm. So the idea here was to look at the dependence of SST and the enthalpy flux, the exchange of heat from the ocean to the tropical cyclone, the dependence of these on the intensification rate. So the x-axis is the intensification rate threshold. Take all values greater than this threshold. And the y-axis is the anomalous mean. So we're taking the mean value for the certain subset above this threshold of intensification rate, and we're subtracting the mean value for all conditions, for all intensification rates. So it's an anomaly with respect to all the mean of all the values. As you would expect, as you increase this intensification rate on the x-axis, you get an increase in the pre-storm SST, the blue curve. And the dark circles are where it's significant at 95%. So this is what you'd expect. You need, especially for the storms that are intensifying more rapidly, it's critical that they have a high SST to fuel the intensification. and also the enthalpy flux increases, the red curve. But it's only significant for basically for rapid intensification, at least 25 knots in 24 hours. So this is saying that it's really critically important to have a higher enthalpy flux, mostly for these rapidly intensifying storms. And then the gray shows the SST cooling caused by the storm, and there's a significant reduction in the cooling caused by the storm itself. So if you add up the blue and the black curves, so this is kind of the effective SST that the storm feels, that will give you an indicator of the impact of the ocean. So the idea is that salinity can reduce this SST cooling under the storm, and this can have a potentially big impact on the SST and the enthalpy flux to the hurricane. So where do we expect salinity stratification to have an important impact on rapid intensification? This shows a measure of the importance of temperature versus salinity to density stratification in the upper 100 meters. And to calculate this, for the temperature contribution, we took the regression coefficient between the normalized temperature stratification and the normalized density stratification. So if this value is 1, it means there's a perfect correspondence between temperature stratification and density stratification. And in a lot of the regions in the Western Atlantic, Caribbean, and Gulf of Mexico, it's close to 1. So temperature stratification is very important. And then we did the same thing for salinity. And the bottom plot shows that there are also a lot of areas in this plume region, the Amazon Orinoco plume area, in the Eastern Caribbean and Western Atlantic, where salinity is also very important in terms of density stratification. So this is where we would expect salinity to have the biggest impact on hurricane intensification. Okay, so focusing on the Western region. So the main result here is that in this region, ocean temperature is important for rapid intensification, and salinity is not. And that's not too surprising because temperature dominates stratification in this region. And the lower plots here show the anomalous means, again, for this is using HERDAT tropical cyclone tracks and intensities and a HICOM reanalysis daily data for the ocean. And for all intensifying storms, greater than 5 knots, basically greater than 0, all intensifying, there's no significant difference in these ocean parameters, tropical cyclone heat potential, temperature, density, salinity stratification, or sea surface salinity. So the ocean doesn't matter a whole lot for the ones that are intensifying more weakly. The bottom shows rapid intensification, and now the heat content, tropical cyclone heat potential, is significantly higher for rapidly intensifying storms compared to overall. And salinity stratification plays very little, no significant differences in salinity. So that's consistent with what we would expect. In the eastern region, so it's the opposite in the eastern region. Ocean salinity is important for rapid intensification, and temperature is not. So again, the top shows all intensifying storms, and there's basically nothing, no significant predictor. And if we look at RI specifically, now temperature, heat content temperature stratification is insignificant, and we have significantly lower sea surface salinity, higher salinity stratification, and higher density stratification as a result. So this suggests that salinity might be a useful predictor, at least in this eastern region. So that was just a statistical analysis. We also ran a one-dimensional ocean model to partially test these results. We used the PWP model, which can be initialized with temperature and salinity profiles, and then forced with surface wind stress, heat flux, and E minus P. We set the heat flux and E minus P to 0 because we want to look at the ocean mixing impacts. At each time step, entrainment occurs when the bulk Richardson number is unstable, less than 0.65. It entrains successively deeper layers until it's stable. And then it mixes at each step until the gradient Richardson number is greater than 0.25. So it keeps mixing to make it stable. We use kind of an idealized axisymmetric tropical cyclone wind field. So it is zero at the eye, and then it increases to the eye wall, and then decreases radially outward. Function of maximum wind speed, radius of maximum wind speed, translation speed, and distance from the storm center. We take a 50-kilometer radius of maximum wind, a translation speed of 5 meters per second northward, which is about the average maximum intensity, maximum wind of 60 knots for the control. And then we do experiments where we decrease it to 20 knots at the southern eye wall. So it goes from 60. And then when you get to the second eye wall, it's going northward. It gets to, by the time it passes, the second eye wall passes, the intensity is down to 20 knots. We do another experiment where it decreases only to 40 knots, and then two where it intensifies, 1 to 80 knots and 1 to 100. So we initialize it with 20 different profiles from Argo floats. And the reason for doing this is to get an ensemble of model results, to get an idea of uncertainty. These profiles are from the Amazon Orinoco region in the Western Atlantic during August, October, the peak of the hurricane season. We do model simulations, 2 different experiments. So one in which we used the actual temperature and salinity from each of these profiles, and the other where we used the temperature stratification, but set salinity to a constant as a function of depth. So this gives us a total of 200 simulations. We had 5 different intensification rates, which I described in the previous slide, 20 different temperature and salinity profiles from the Argo floats, and 2 different experiments, one with salinity stratification and one where there's no salinity stratification. And what we want to look at is, for differences in intensification rate, are there differences in the impact of salinity on SST cooling? The observational statistical results suggest that as you increase the intensification rate, the importance of salinity increases. The decrease in the cold wave magnitude, that muting of the SST cooling increases as the intensification rate increases. So that's what we're testing. And these show the results. So the left here shows the locations of all the Argo float profiles that we use to initialize the model, the colored squares. And the shading shows mean surface salinity during August through October. So most of them are in this river plume region where the salinity is low. The underneath shows the salinity profiles from each one of these floats. And most of them have strong salinity stratification in the upper 40 or 50 meters. The upper right panel shows the wind forcing that we use for each experiment. The green is the control, 60 knot maximum winds. And so then the blue and the red are the experiments where we reduce the intensity. The purple and black, we increase the intensity. And the bottom right shows the results. So as the intensification rate increases, the blue is the minimum intensification rate. They actually decrease in intensity. As you increase the intensification rate going from blue to black, you do get an increase in the reduction of cooling. So this muting of the storm-induced cooling increases as you increase the intensification rate of the storm. So this is consistent with the observational results. All right, so the final step is to see if salinity can actually improve a forecast, at least a statistical hindcast, you could say. Is there potential for salinity to improve detection of rapid intensification? So for that, we do a binary classification. So we want to know if there's going to be rapid intensification or not. Two outcomes. And we use logistic regression. So you can think of this as similar to linear regression, except we're just predicting the probability of one of these two outcomes, the probability of rapid intensification, based on different predictors. So we use something called balanced class weight. So if the probability, for example, of rapid intensification is 5%, we penalize the model 19 times more for incorrect prediction of RI. So if it doesn't predict RI and RI actually happened, then we weight that 19 times more than if it predicts RI and it doesn't happen. And the reason to do this is that if we didn't, then the model would just basically always predict no rapid intensification, and it would have, it would be right 95% of the time. So this predicts the probability of RI occurring given the values of the 10 different predictors that I described earlier, the 2 ocean persistence and the 7 atmospheric predictors, scaled from 0 to 1, like I mentioned, based on maximum and minimum observed values for which RI occurs. So just another example, so if you have maximum minimum values ever observed during RI for SST, let's say they're 30 and 26, any SST above 30 is set to 1, anything below 26 is set to 0 before using in the model. And then we divide into the RI cases and the non-RI cases based on the 6-hour storm locations, which is 55% for the training set, and then test on the remaining 45%. We've repeated it using different percentages, test the sensitivity. We repeat 100 times, and this is to get an idea of the uncertainty associated with the training and the testing sets. Okay, so that's kind of the control case, and then we repeat the whole thing, and we add surface salinity as an 11th predictor onto these other 10 that are already in there. And we test the significance of the difference in predictability between the standard control model and the one where we've added sea surface salinity to see if there's any significant increase in skill by adding salinity. So to do this, to test the skill, we have some metrics that we use. So the basic ones, true positives, model correctly predicts RI, true negative, correctly predicts no RI, false positive, incorrectly predicts that there'll be RI when there's actually not, false negative, incorrectly predicts that there's no RI when there actually is. And then we can derive some metrics from these. So the false positive rate is the number of times it predicted RI divided by the total number of times that it falsely predicted RI divided by the total number of times that RI did not happen. So you want this to be low. Probability of detection, which I mentioned before, the probability of the number of times it predicts RI divided by the total number of times that RI actually happened. You want this to be high. False alarm ratio, you want it to be low. False predictions divided by the total number of times that rapid intensification was predicted. And so then there's a more exotic one here, area under the curve. And this is where you plot the probability of detection versus the false positive rate on the x-axis. And you can vary this, vary the model, the discriminant threshold. So the model predicts the probability that RI will occur, and then we convert this probability into a 0 or a 1, whether RI will happen or not. And the standard is to use 50%. If it's above 50% probability, you say that RI will happen, and if it's below, you say it will not. But this threshold could be anything. So as you vary this threshold, you can plot the probability of detection versus the false positive rate. And the idea is that you would hope that as the false positive rate goes up, the probability of detection goes up even more, and that will result in a big area underneath this curve. So the higher the number of this, the better your skill is. And the final one is the Breyer score, which is just the mean squared difference between the predicted and the actual outcome. So in the next slide, I'll show the results in terms of these last four skill metrics here. And so these are the results. And the basic thing is that we do see a significant improvement when surface salinity is included as a predictor. The ones in blue show where we use high competency surface salinity to add to the model. And there's a significant increase in probability of detection, a significant decrease in the false alarm ratio when you add salinity. The area under the curve goes up significantly, and there's a reduction in the Breyer score, although it's not significant at 5%. So we did the same thing with satellite sea surface salinity for a slightly different time period, and the results are similar. The probability of detection goes up significantly, false alarm goes down, area goes up a little bit, and the Breyer score goes down significantly. So this is saying that potentially, if you add salinity to a RI detection scheme, there's the potential that it could increase predictability detection of rapid intensification. Okay, so conclusions we found in the Western Atlantic and Eastern Caribbean, sea surface salinity is significantly lower and salinity stratification significantly higher for tropical cyclones that undergo RI compared to those that do not. We think there are two main reasons. One is the enthalpy flux is very sensitive to SST as tropical cyclone intensity increases because the winds get a lot stronger, so that the storm-induced SST cooling can become very important. And intensifying storms, rapidly intensifying ones especially, cause more vigorous mixing as the intensity gets higher, so that subsurface ocean conditions can have a bigger impact on the TC-induced SST cooling. If the intensity is very low, there's not going to be enough mixing for the stratification to matter. As you mix deeper, you have the potential to mix up colder water, but if there's salinity stratification, then probably it won't mix up as much colder water. And we found the inclusion of sea surface salinity in a statistical RI prediction scheme may be able to improve the prediction of RI events in the Atlantic. So those are the main conclusions. And the future work is to test salinity in an operational version of ships, the ship's rapid intensification index, to incorporate maps of ocean dynamic temperature into AWIPs used at National Hurricane Center. And the dynamic temperature is a vertical average of ocean temperature from the surface to a variable mixing length. And this mixing length depends on stratification, which can include salinity. So this is a little bit different than just taking the heat content in the upper ocean, for example. And these efforts are part of a 2-year proposal funded by the Weather Program Office Joint Technology Transfer Initiative with Hurricane Research Division, John Kaplan of the National Hurricane Center, and Colorado State University, the NOAA Cooperative Institute. This will begin in October. Also, we're working on a satellite-derived dynamic temperature data set, which is a paper now that's in revision, part of another proposal. Another question is whether salinity is important for rapid intensification in other tropical cyclone basins. We only looked at the Atlantic. There are other areas in the world ocean where there can be significant surface salinity signals. So it'd be interesting to look at these other basins. And another one is, in general, how important are temperature and salinity stratification for storm-induced cooling? What if there's salinity stratification, but there's no barrier layer, no separation between this salinity stratification and the base of the isothermal layer, for example, and what's the balance between kind of the dynamic and thermodynamic effects of changes in temperature stratification. Changes in temperature stratification will tend to decrease the efficiency of mixing, decrease the mixing rate as you increase stability, but it can also increase the amount of cold water that's mixed up and is available to cool SST. So what's the balance between those? And Lev Looney has started looking, he's a PhD student at Rasmus, has started looking into this. Okay, one other thing, we plan to incorporate this ocean dynamic temperature, which accounts for salinity and temperature stratification, into AOML's real-time display. This is a nice display here that shows a map of where conditions are conducive to tropical cyclone intensification in general, in terms of the ocean. So it has SST, tropical cyclone heat potential, and salinity. We'd like to add this in to get a more quantitative indicator. And finally, we have some current and planned hurricane observations that we hope will help to understand tropical cyclone ocean interactions a little better. Ocean gliders, which are ongoing. This shows 2019 tracks, for example, and the temperature and salinity. So you can notice very strong salinity stratification from this glider in the Caribbean. So already papers have been written. Ricardo and others have written papers about the importance of salinity and importance of these measurements like this for improving hurricane forecasts. We have a plan to deploy several sail drones into the Western Atlantic and Caribbean during next hurricane season. This is what they look like in the bottom right, and they measure SST, surface salinity, ADCP on them, and atmospheric parameters. And the idea is to track them with gliders, the orange rectangle here, and then if there's a hurricane passing close by, direct it up to the hurricane, do a little observation pattern ahead of it, and then put it right through the center of the hurricane, and then do some measurements afterwards. So we're planning to test these especially designed sail drones that can withstand these strong winds. We plan to test these and see how useful they are, see what kind of data we get, and to potentially do this more regularly in the future to help understand and predict hurricane intensification.